if you're working in Rust, chances are you're chasing performance. You pick the language because it's designed for speed, but turning that potential into actual real-world speed requires digging into things like configuration flags, memory layout, tools you probably haven't even touched yet.
Exactly. And welcome to the deep dive. Today we've gone through the Rust Performance Book, and we've pulled out the most specific, actionable advice. Our mission here is really to distill those advanced strategies for you.
Right. We're trying to give you the blueprint to move beyond just beginner-level optimization.
It's the shortcut, really.
Yeah, the shortcut to making your code truly fly. We're talking improving runtime speed, cutting down memory usage, shrinking that binary size, and maybe, just maybe, making your compile times a little more bearable.
And we're focusing on techniques that apply to what the community calls hot code.
And that's a really important distinction, isn't it?
It's the core philosophy. I mean, optimization is a cost. It takes time. And it should only ever be applied to code that runs so often that tiny improvements actually add up to something a user can feel.
Right. If your program is spending 99% of its time waiting for a network response, optimizing some math function that runs once is.
Pure vanity, a total waste of time.
Okay, so let's unpack all this. We're going to start with the lowest effort, highest impact changes. This is the stuff that requires zero code modification. Just flip in the right switches.
The biggest speed multiplier you're going to find is right there in your build configuration. And the single most important step is just making sure you use the release profile. You absolutely must use that release flag.
It sounds so basic, but I feel like a lot of people just don't realize how fundamentally different a debug build is from a release build.
Oh, it's night and day. Dev builds are the default for a reason. They're for quick compilation and good debugging, but that means they skip all the aggressive optimizations.
And they have other things too, right? Like assertions and checks.
Exactly. They include debug assertions, and this is a big one. They perform integer overflow checks on every single operation.
So they're basically carrying around all this extra safety luggage everywhere they go.
That's a perfect way to put it. And disabling all that luggage by switching to a release build, it commonly yields, 10x to 100x speed up.
That's 100 times.
It's the kind of gain you will never, ever achieve with handwritten micro-optimizations. And look, if you find all the build settings overwhelming, you can look at tools like Cargo Wizard. It sort of encapsulates the community's best practices for you.
Okay, so once we've committed to that release build, we immediately hit that classic problem in all performance engineering, the great trade-off.
Speed versus compile time.
Exactly. Maximizing runtime speed often just tanks your compile times. So how do we approach that balance?
We have a few levers we can pull. One is codegen units. By default, the compiler breaks your crate up into multiple units to compile in parallel. That makes builds fast.
Which is what you want for development.
Right, but if you set codegen units equal 1 in your release profile, you're telling the compiler to look at the whole program at once. This, it definitely increases compile time, but it lets the compiler do better cross-function optimization, which can boost runtime speed and even shrink the final binary.
So we're giving the compiler more homework, and in return, it writes faster code for us.
Pretty much. And the ultimate expression of that idea is link time optimization, or LTO.
Right.
This is a whole program optimization technique that can squeeze out another, say, 10 to 20% performance gain on top of everything else.
LTO sounds like serious business. I know there are a few different flavors of it. How would you choose between them?
So you start with thin local LTO, which is the default for release builds. It's pretty lightweight. And you can move up to thin LTO. That allows optimization across crate boundaries, which is a big deal, but it does it in a way that's still pretty efficient.
Okay, but what if I need every last drop of performance?
Then you go for the final boss, fat LTO. You set LTO cool fat. This is the most aggressive option. It has the best performance, but by far the worst compile times.
And why is it so slow? What's it doing?
The compiler is effectively pulling your entire program, every crate, every function into memory during the linking phase to do this massive global analysis. It finds optimizations that no local step could ever see, but it takes a huge amount of memory and time.
That makes the trade-off loud and clear. If I'm on a CI job, I probably want thin LTO. But for the final production binary, maybe I spring for fat LTO.
That's a very smart approach. Okay, let's shift away from compilation flags for a second and look at memory. We can get huge wins by changing something really fundamental, the global memory allocator.
Wait, you can just swap out the operating system's memory manager? Why would you even want to do that?
Well, the default system allocator is a generalist. It's built for robustness and low memory overhead in a, varied multi-user environment. But alternative allocators like Gemalloc or Mimaloc are specialists.
Specialists for what, exactly?
High concurrency workloads. They're optimized for situations where you have many threads all trying to allocate memory at the same time.
Ah, so they're better at reducing lock contention.
Precisely. They minimize those synchronization points, which are often the bottleneck in a heavily parallel Rust app. Using one of these, especially Gemalloc, with transparent huge pages on Linux, can really improve your runtime speed and memory stability.
Okay, one last build configuration trick. What if I know my code is only ever going to run on my brand new machine with the latest chip?
Then you can unlock instructions that the generic build has to ignore for compatibility. You use the flag nasc target C punitive.
And what does that do?
It tells the compiler, hey, use every advanced fast instruction that's available on the machine you're compiling on. This includes newer SIMD instructions like AVX, which let the CTU process multiple pieces of data at once.
That sounds amazing, but
Right.
what's the catch? What if I compile on a new server with, say, AVX 512 and then deploy that binary to an older machine that only supports AVX 2?
You've just created a huge maintenance headache for yourself.
It'll just crash.
Yep. The OS will often just fail to load the program entirely. You'll get a cryptic illegal instruction crash. This flag is only safe if you can 100% guarantee your target environment is identical to or newer than your build environment.
So it's another one of those trade-offs. Maximum speed today versus maximum portability forever.
The classic trade-off.
Okay, that's a huge list of flags and configurations. But as you said at the start, making these choices requires measurement. How do we make sure we're not just chasing phantom gains?
Measurement is gospel, and let me be clear, mediocre benchmarking is far, far better than no benchmarking at all. You need a reliable way to answer the question, did that change actually speed things up?
What are the go-to tools for that?
In Rust, we have crates like Criterion and Divan for micro-benchmarking. For more general stuff, Hyperfine is excellent. But you have to think about the metric you're using. Wall time, what a user sees, can have really high variance.
Because of the OS doing other stuff in the background?
Exactly. So for comparing small changes accurately, metrics with lower variance, like cycle counts or instruction counts, are often more reliable.
So benchmarking tells you if you got faster. Profiling tells you where you should be focusing. How do we find those hotspots?
Profiling finds where that 80% of your execution time is being spent. I remember once spending hours optimizing a function only to realize from a profiler that it ran like 3 times during the entire application's lifetime. A total waste.
So you profile first, always.
Always. Tools like DHAT are great for finding hot allocation sites. Cache grind or call grind can give you instruction counts. And for a really nice visualization, Samply is great. It produces that Firefox profiler view a lot of people are familiar with.
And if we're profiling a release build, we need to tweak the config again, don't we?
We do. To get useful info from optimized code, you need 2 things. First, enable line-level debug info with debug, line tables only. Second, and this is crucial, you have to force the compiler to use frame pointers with nary-C force frame pointers.
Like without that.
Your stack traces will be garbage. You won't be able to map performance costs back to specific lines of Rust code.
Okay, we've covered configuration and measurement. Now, this is where it gets really interesting for me. Let's talk about the techniques for avoiding the single most insidious cost in many programs: heap allocations.
Heap allocations are moderately expensive. They usually involve acquiring a global lock, messing with some complex internal data structure, sometimes even a system call. If your profiler shows malloc or free using a lot of time, you have to reduce your allocation rate.
And the standard VEC is probably the first place people run into this.
It is. VEC grows quasi-exponentially. It goes from 0 to 4 to 8 to 16 elements. For a very short vector that maybe only holds 1 or 2 things, that first heap allocation is completely wasted effort.
So for those many, many short vectors, what's the solution?
The solution is small vec-D.
Okay, tell us more about small vec.
Yeah.
How does it avoid the heap?
Small vec uses what's called in-place storage. It basically embeds a little array right inside the vec struct itself on the stack. If you never put more than n elements in it, you never touch the heap. No allocation, no lock, no syscall. If you do go over, it just seamlessly spills over to the heap like a normal deck.
And what if you know the maximum length for sure?
Then ArrayVec is even faster because it's guaranteed never to allocate on the heap. It's array speed with a vector-like API.
And for vectors that are definitely going to be long.
Then you have to be proactive. Use vec.withCapacity or vec.reserveExact right at the start. Make one big allocation instead of 4 or 5 small ones with a bunch of memory copies.
What about reference counting types like RC and ARC? People worry about the cost of cloning them.
Right, but cloning an RC or an ARC does not do a heap allocation. It's just a very fast atomic increment. That's a crucial distinction. The real cost is that you're forcing the initial value onto the heap in the first place, which you might not have needed to do.
We should also talk about clone from. That seems like a hidden gem.
It's totally overlooked. If you have two vectors, A and B, and you do a dot clone from MB, Rust is smart. It checks if A already has enough capacity. If it does, it just reuses A's existing allocation instead of throwing it away and making a new one.
Another clever tool is the cow type, clone on write. Could you give us a real-world scenario where that saves you?
Okay, imagine a config parser. Most of your values are static defaults, right? Like a server name, localhost, which is a static str, no allocation needed. Cow lets you wrap that in a cow borrowed.
So for most users, it's zero cost.
Exactly. Then, if a user does override that value and you need to own it, you call cow.tomut, and only then does it do the allocation and copy. It's efficient for the 99% case.
That seems incredibly useful. Let's talk about a common pitfall, reading lines from a file.
Ah, yes. The buffread.lines trap. It's so convenient, but it allocates a brand new string for every single line. If you're processing a million-line log file, that's a million allocations.
Ouch, what's the fix?
The fix is simple. You loop manually with buffread.readline. You create one workhorse string outside the loop, pass a mutable reference to it, process the line, and then just call line.clear at the end of a loop. You go from a million allocations down to maybe a handful.
Let's switch gears to specific data structures, starting with hashing. The default sci-hash is known to be a bit slow. Why is that?
It's not slow because it's badly written. It's slow because it's robust. Sci-hash is designed to give you strong protection against hash DOS attacks.
Right, where an attacker sends crafted keys to cause tons of collisions and bring your service to a crawl.
Precisely. The complexity needed to avoid that is what makes it slow, especially for short keys like integers.
So if my profiler says hashing is a bottleneck, and I know my input is trusted, should I switch?
If security isn't your primary concern, then yes, switch. You have alternatives like Rust allocache, which uses FX hash. It's very fast because its collision protection is, frankly, terrible. But for trusted integers, it's incredibly fast.
And what's the risk there?
The risk is you forget why you did it. In one test, switching back from Xhash to the default sci-hash caused slowdowns from 4% all the way up to 84%. The speed difference is massive, but you are deliberately lowering your security posture.
Next up, size. Why does the physical size of a type matter, even if it's on the stack?
It matters because of how things get copied. Specifically, types larger than 128 bytes are usually copied with an external function call, memcopy. Smaller types can have their copy code inlined directly by the compiler, which is much, much faster.
So for any hot type that gets copied a lot, we want it under that 128-byte threshold.
You do.
What are some good tricks for shrinking those types?
A really clever one is for enums. An enum is always sized to fit its largest variant. If you have one variant that's way bigger than the others, say for a complex error, you can box one of the fields inside that variant.
Ah, so you move the big data to the heap.
Right. The enum itself now just has to store a small box pointer on the stack, which can dramatically shrink the whole type.
So the enum becomes smaller and faster to copy, even though you added a heap allocation for that one rare case.
Exactly. The benefit to the hot code often outweighs the cost. Another easy one is converting a vec you won't resize. A vec is 3 words: length, capacity, pointer. If you use vec.intoBoxedSlice, it becomes a 2-word boxed slice, length and pointer. You just shrank your struct by 8 bytes.
And how do we stop these types from accidentally growing over time?
Static assertions. You use a crate like static assertions to literally write a test that fails the build if a type's size changes. Assert a size. My hot type 64. If someone adds a field, the build breaks. No silent performance regressions.
Are there any standard library gems we should mention before we move on?
Yes. Always use the else variants of methods like option.occurelse. They compute the error value lazily inside a closure, only when it's actually needed. Also, it's worth benchmarking the parking lot crate as an alternative to the standard library's mutexes. It can be a lot faster for certain workloads.
Finally, let's talk about the developer experience tax, compile times. We know about LTO, but what else can we do?
Start with the easy fix that has zero trade-offs.
Hmm.
Use a faster linker. On Linux, you have options like mold or wild that are often significantly faster than the default. It's a free win.
A free win is always good. What about when the problem is in the code itself?
That's usually one of two things, macro bloat or LLVM IR bloat. For macros, you can use the nightly flag -Zancro stats to see which procedural macros are generating thousands of lines of code. If you find one, maybe replace it.
And the IR bloat.
That's almost always from heavily generic functions. When the compiler instantiates a generic function for 5 different types, it makes 5 copies of the underlying code. If that function has a lot of boilerplate that doesn't depend on the generic type, you're compiling that boilerplate 5 times.
And the fix for that?
You refactor. You pull all the non-generic logic into a private non-generic inner function. The public generic function becomes a tiny wrapper that just calls the inner one. That inner function only gets compiled once. std.fs.read is a classic example of this pattern.
Wow. We really went from simple command line flags all the way down to refactoring based on how LLVM works. That's the full spectrum.
It is, and the final advice is always focus on algorithms and data structures first. An ON log n algorithm will always beat a cleverly optimized ON squared one. But once you have that right, all these small speedups, they really add up. Every allocation you shave off, you're stacking the deck in your favor.
So to wrap up this deep dive, we'll leave you with this final provocative thought to take back to your own projects.
If you haven't benchmarked your program's performance characteristics, what critical, easy speedup like ensuring you use a fast linker or avoiding that allocation trap in file I/O are you currently overlooking? Use Cargo Wizard as a starting point, get some configurations to test, and start measuring today. That measurement is the only path to true speed.